Hi everyone, this is Mr. Robotic Warfare, and today I've got a new Redstone design that I'd like to show off. Breaking the theme of the past couple of videos on this channel, this is in fact not an adder. I've moved on to a different kind of device to be working on in my quest to continue towards building a fully working Redstone computer without any redstone. It's not entirely accurate to say that I've moved on, though, however, because these RAM designs were actually the very first thing that I worked on when I started doing computational Minecraft. We're going to be looking at version 3 here today, but version 1 I developed in December of 2019, and right on New Year's Day, this was the project that actually got me my invite to SciCraft. So other than just kind of being a technically cool thing to work on, these designs and this project has a special place in my heart. So like I said, we're really only going to focus on the most recent version here. There are some pretty deep technical things that go into how this actually works because it involves instant wire, and I will probably make another longer video to cover all of those things in detail like I did with my last video. So let's get started. So this is a design for a RAM system. RAM meaning random access memory. So what this essentially is a way of storing information in the game in such a way that it doesn't matter how much you have, you can get any individual value stored in the device in the same amount of time. So using a little bit more real-world terms, RAM is a constant time device, which means that you can select any memory address, read the information from there in the same amount of time. This differs from something like a sequential logic system, where if you had to get towards the addresses at the very end of the device, you'd have to go all the way through. A good example of this is if you can imagine items in a chest. If you wanted to use a hopper and essentially have each item stand for some kind of information, if you wanted to get to the item in the very bottom right hand corner of the chest, if you didn't filter it, you'd have to wait for all of those other items to pour out first. This is trying to avoid that. So the idea is that this is a constant time device. Now, this looks a little crazy, and it's definitely not the typical RAM designs that you would see if you're used to computational Redstone. But the cool thing is that from the other angle, this is actually very compact. Because I'm using a special kind of instant wire here, we have these big long tails on either side, but the main trunk of the machine is right here. And this is in fact 16 bytes worth of information contained right here. So there's essentially 8 bits per slice, and I've got 16 slices built up. However, this is using an 8-bit encoding scheme. This center piston here is actually an enable signal. That's not one of the address bits. So with 8 bits of addressing, you can get effectively 256 memory slices that are supported with this machine. So you could actually just take this and extend it further this way, kind of like this guy over here. That's version 2, what we'll get to later. You can see that it's a lot less optimized. But you can store a ton of information with this. In fact, this design right here is storing half a kilobyte of information. So that's 512 bytes, which is a byte, 8 bits a piece. So that's a lot of memory. Just for the demonstration stuff, we're going to be looking at a smaller version of this today. But the general principle behind how this works is that each slice is capable of storing information on these redstone blocks here, which is what I call the platter. It's kind of an homage to hard disk drives, but certainly because this is RAM, it's not the same thing. I just like the term. So you've got this kind of physical platter here where you see your information encoded. And the idea is that we've got pistons here that actually move these redstone blocks up and down, and depending on what position they're in, that either represents a 1 or a 0. In this case, a block being right above the slab here in the down position indicates a 0, and a block in the upwards position here indicates a 1. So for each slice, it holds 4 bits on this side and 4 bits on that side. And in fact, this design is extensible, so you can actually add additional 4-bit cells on each side, 4 bits being a nibble, being one of the best words in computing. So you can continue to add nibbles to either side. As long as you respect push limit, you can do that pretty continuously, obviously at the cost of a little bit of delay. But essentially each slice here also has a platter, but this is for the addressing side of things. So you can see that the redstone blocks here are staggered in such a way that each one of these devices corresponds to a unique address. So right here, because these are all up, if I were to enable this block right here, you would see that this rail would turn off completely, trigger the line beneath it, and that would get us to slice 0 here. If we then switch this and we toggle the first bit, you would see that we now have the second slice, which is completely open, and if we were to disable, or rather trigger the enable signal, we would then get the first slice. So what we're able to do is effectively address to any individual one of these slices, and because this is symmetric, this is actually would work exactly the same way on the other side. So let's just do a quick read operation here. Because we have a bit set here in the 0th slice, we just kind of have a very basic output piston right here. So what we want to do is we would expect when we actually trigger a read, which we would do by hitting the enable signal right here, what we would expect to see is we would expect to see that piston right down there extend, because there's essentially data that is being read out of that slot right there. So let's go ahead and do that. So we can trigger that right there, and if we go down and look, you can see that we do in fact have this data that's been read out there. We're going to do that again here, essentially, because we're essentially undoing the state that we've done, and you can see that it goes right back to the same thing. Now, the other bit that you'll see that I have set here is all the way on slice 16, and in fact, if we wanted to be cool about it, we could do it on a different bit of the output. And now, if we wanted to address slice 16, which technically has an address of 15, we would enter 15 in binary, run our enable signal, and you can see that we've got that that third bit now that's been output. So this actually works in the exact same amount of time. Speaking of which, let's start talking about timing now. So I'm actually going to switch this back just so that we can use the excuse the lag, so we can use the timing setup that I've previously built up. So this entire device, for all 256 slices, if you wanted to make it that large, has a 10 game tick read time. So let's just demonstrate that real fast. So you can see the scoreboard on the right hand side, which you actually can't see. Give me just one moment there. We'll scooch that over. Playing on a widescreen monitor right now. So you can see that propagation delay right there. So if I go ahead and trigger this device, we're reading from the 16th slice there, address 15, and we want to see how long this is going to take. So if you watch the numbers very closely, you're going to see that we go from 17 to 27. So that is 10 game ticks right there. Do it again, 21 to 31. And now if we go back to the first slice here, we're now reading off of this 0th slice. We do the same thing, and we can see 85 to 95 and 30 to 40. We've got 10 game ticks as a constant time device completely throughout this entire machine. And like I said, because this is using instant wire, if you would extend this all the way to the 256 limit, as long as you got everything loaded, you would have exactly that same 10 game ticks. So this is effectively giving you access to a huge amount of information very, very quickly. Now, it's a little bit large, but you kind of need to do that to make sure that you can deal with rails and instant wire and all that kind of thing. Obviously, you could stack this closer together if you didn't use instant wire, and in fact, that's what version 1 and version 2 of the machine were using. The issue there, obviously, is that rails have a limit of how far they can go, and every 9 rail tiles, you would need an observer, which means that you now no longer have a constant time device, because an observer on the address tray, as you continue on, would mean that information farther in the back, it would take longer for that signal to reach them, and therefore it would take longer to actually read that memory. So that technically would not be considered RAM. So that's just a quick overview of the reading process. Now let's talk a little bit about writing. So like I said, the pistons over here are supposed to move each of these blocks up and down. The way that this works is that this right head, I call this the read head, this is the right head, that right head is pushed over when a slice is actually activated. So let's go ahead and do that really fast, and then I will just disable the auto return so you can actually see what's happening here just by breaking that trapdoor. So if we were to go ahead and trigger a read operation, or in fact, essentially an enable operation, it will automatically read out. So when you actually send an address to this device, to minimize the time that it takes to get a readout, it'll just instantly send that read. So you can see that we've got that bit set right there. But the other thing that's happened is that my right head is slid over. And we've got more pistons over here on the top that are actually positioned to move these redstone blocks up and down. But by default, they are moved over such that if these pistons extend, they don't do anything. However, when we've got them moved over and the slice is actually active, we could go ahead and reset this one right here. And you can see now that we had both of these set. That one didn't move at all, but this one did. So now we've actually got this set, and I'll demonstrate that again by moving it back up. That one stayed in the exact same place. So because this is the only slice that's enabled, this is the only one that we're reading and writing to. Just to demonstrate that again, I'll reset this read here. We could send a signal on this path to get that bit written now, and then we could also just go ahead and return the right head. Obviously, you can really tighten up the timings for these things, but right now I just have it set in a manual way so that we can actually see what's happening. So now if I were to essentially disable this, which would in fact trigger another read, what you'll see is that we've got now our new information that has been sent to the output. So one of the really complicated things with trying to do writes like this is that when you are dealing with one redstone ticking pistons, it's using the block dropping effect, right? So if I were to trigger this, it's going to drop its block through an observer with a 2 game tick pulse, as opposed to something like a redstone block where it's actually going to hold onto that block. Obviously, you can break it and place it more quickly to get that same effect. But the issue here is that because we are trying to do this systematically, we cannot assume any a priori knowledge of how the platter is set. So when it's time to write to something, it's difficult to do that with pistons because you don't necessarily know what state that they're in. So if it's in a 0 state and you need it to get to a 1 state or vice versa, that's pretty easy. You just trigger it. But what if you're trying to go from a 0 to a 0 or 1 to a 1? There's no change that actually needs to happen, but if you send a signal anyways, you're going to get undesired behavior. Well, how do you prevent that? You would need to know beforehand how that works. So one of the other ways that this works is that when you actually do the writing process, this machine is enabled in such a way that it does what's called a destructive readout, which means that when it reads the data out of the platter here, when you've got the writing head enabled, which is this guy right here, it will actually automatically reset that. So the read is getting looped back into the write, and you're essentially rewriting the same value to that cell that already has it. And in effect, what that's doing is triggering those pistons and resetting the heads. So the actual full write process here is enable the destructive readout, enable the machine to trigger a read. That read then gets sent back around and rewrites the cells to all zeros, and then you can actually send in the signal that you want to write later, and it will be appropriately processed. So just to demonstrate that here, you can see that we've got these two bits set here. I'm going to enable the destructive readout, and we're actually going to slow the game down too. Let's go nice and slow. So what's going to happen is we're going to enable the machine. The slice is active. The read happens. It gets sent back up, and you can see now that the 0 slice is now completely reset. And it is reset in such a way that we can now write the data that we'd like to have stored on the head. We can then re-trigger the device to go back, and then disable the destructive readout so that it doesn't essentially get deleted when we do the second read for the state. You could then reset these guys, and then when you disable the machine again, we're going to have that new information that is now nice and locked in. Now, obviously, this reading out system with these pistons here is just notional. A lot of this stuff is devoid of any timing or specific use cases here. So there's obviously, latitude here in terms of how you could actually get this design. But this is the core concept. And it works, like I said, by translocating redstone blocks and having them move in different ways. I will just explain briefly how this is actually working, because if you're looking at this and you don't know what's happening, it can be very confusing. How am I actually getting any signal here? So this is a very special kind of instant wire that some of the folks on the SciCraft server developed for me. Chiefly To Know To Name was responsible for designing a brand new type of instant wire just because I asked nicely. So shout out to him. But what's actually happening here is that we have a redstone, or excuse me, a rail line up here that will process block updates. So if I were to place a block, you can see that this whole rail line is going to pulse. And in fact, you can actually detect that. Now, the cool thing about this instant wire, which makes it special, is that you can update it anywhere on this top rail and it won't break. For those of you who have worked with instant wire, you know that it's fairly fickle and it's very easy to break. This is actually pretty robust. It's not completely spammable, but it's mostly spammable, which is nice because that means you can get this machine working pretty fast. So like I said, over here you can see the same effect too. If I update that, that's what's actually reading it out. Now, the question is, well, that works well and good if you're placing or removing a block directly next to the rail, but this piston is just moving over. That's not happening at all. So one of the interesting things about rails is that when you change a rail's power state, I guess we'll just do this down here just to demonstrate. When you change the power state of a rail, it will actually send a block update to any rails that are directly below it. So if you have a rail right here and this rail changes power state, it actually does send an update to this rail right here. Obviously, because it's not powered, it's not going to realize that. But if we were to bud this rail, for instance, and then power this rail, this would actually re-update itself and unbud itself because it's essentially being issued a block update to check for whether or not it's powered. So that's how this works. When the redstone block is in the down position, this rail right here is powered because it's on this redstone block. And when it gets pushed over by the piston here, if this redstone block is still right here, it's going to stay powered, right? So it goes from powered to powered, which means that it doesn't change state, which means that it doesn't issue any update, which means that the instant wire doesn't detect anything. However, if this block is pulled up into what is effectively the 1 position, it means that when you push this over, this rail is going to go from powered to unpowered, and therefore it's going to change power state, send a block update to the rail beneath it, and that's actually going to be detected by the instant wire as essentially the output. So this is a very, very clever way that the other SciCraft folks helped show me in terms of how to do this. There's a whole bunch of people that were involved with this. To Know I Know, FX Process was involved for a little while. Oreo was involved. There were a lot of folks that helped me out with this. So once again, big thank you to the SciCraft server. But that's what I've got. So obviously more information incoming about how this stuff could possibly be used. Get it back to daytime here. And just as a little sneak peek of what this is eventually going to turn into, if you strip away all of that right head stuff, you get effectively a ROM instead of a RAM. And if you do that, you can use it as instruction memory. So what I've got right here in front of this is a program counter, and essentially it's a binary counter that increments as it goes. So this is, for me, the very first stages of building the full computer, having instruction memory tied to a program counter, and then there are some cooler full computer things happening over here that I'll show off at a later date. But for now, that's all I've got. So thank you very much for watching, and I'll see you later. Thanks.